Hello, and thank you for watching my video. Picking up right where we left off at the end of part 2, I wanted to do this video with a bigger example, and the example of 16, because it's a fourth power, and so it's easier to show what's going on. And so we're going to construct a multiplication table labeled up to 16. Recall that the first column plus the area under the real curve y equals n over x has total real area n plus n times log n. So if we wanted to get rid of that leading n term, we could take away the first column, but here what we do when we symmetricize the log function is we take away that n with the radical n by radical n square box. And so we get the wings, which are mirror images of each other, symmetric about that single point at x equals radical n, y equals radical n. So by considering the wings and only the wings, we are effectively dealing with the plain log function term. So here each wing, red wing here, has an area of n log n over 2. And then if we divide the whole thing out, or divide it out by 16 equally, well, x over 4 times y over 4 equals 1. Then we have the symmetric version of our log function, which is just the wings. Eliminate the 1. Remember, the area was 1 plus log of n. So now we just eliminate the 1, and our wings have area log, are the log function, the symmetric log function, a symmetric log function. If we're dealing with an n whose square root is irrational, then we would need to make some adjustments to that little area near the diagonal axis, that point there, to fix that square, if you want to deal strictly with rational areas. For any finite n, the gamma we would compute is just a convergent to it, So, but the point of this is that because the square root graph fits inside the area excluded from the square graph, or the times 16 graph, these areas are exactly scaled by n. So this red estimate of, or convergent to the quantity 1 minus gamma, multiply it by n, in this case 16, and you're going to get the purple area, the 1 minus gamma, the n times 1 minus gamma. But it's going to be the exact same modular structure. So the square root of any n is always going to give you the smaller diagram that fits inside the box, which is excluded by definition from the wings. So rather than, after taking the square root, dividing it by n, why not take the square root again? We can take the square root all day long, and we'll approach 1 eventually, very quickly for low numbers, but we'll never actually get there. And if we did, then we would be at log 1, which is 0. So we don't have to go right to the log function right away, which is what we get when we divide by n, and instead divide by the square root of n, as distributed evenly, x divided by the fourth root of n times y divided by the fourth root of n equals n over the square root of n, aka the square root of n. Note that if we did that here with what you see on the screen, the smaller red curve would not have a point at 1. It would have a point at 2, the square root of 4. So this is something different than the linear scaling that we've done so far. But if we do it all day long, just keep taking the square root, taking the square root, taking the square root, and keep filling in that ever smaller little square in the lower left corner, we eventually do reach the lattice point x equals 1, y equals 1. We just fill the space differently. In this case, an infinite series of self-similar pairs of wings that nest inside each other like Russian stacking dolls. Let's take a closer look at that in the next video. For the time being, thank you again for watching my video. Please like and subscribe, and please click on the PayPal link in the description and contribute to support my research and production of these videos. Thank you very much. God bless you.